Core. The core is the sun's center, and it is where the whole story begins. This is the only place in the sun where nuclear fusion can happen in a stable way. Fusion means tiny hydrogen nuclei are forced together so strongly that they join and become helium. That process releases enormous energy, and that energy is the real source of the sun's light and heat. The core is incredibly dense and extremely hot. The temperature is about 15 million Kelvin, and the pressure is so high that atoms cannot stay normal. Matter in this region becomes plasma, which is a superheated gas where electrons move freely instead of staying attached to atoms. At this depth, the sun is not glowing like a surface lamp. It is acting like a giant fusion engine. What happens in the core does not rush straight out into space. The energy starts here, but it takes an extremely long time to work its way outward because the sun is so dense inside. A photon, which is a small packet of light energy, does not travel in a straight line from the center to the surface. It gets absorbed and re-emitted over and over again, so the trip takes a very long time. The core is small compared with the whole sun, but it does all the heavy work.
Radiative zone. Outside the core is the radiative zone. This layer gets its name because energy moves through it mainly by radiation, not by rising and sinking motion. The material is still very hot and very dense, so energy cannot simply stream outward in one clean path. It has to pass through layer after layer of particles as the sun slowly carries the core's output toward the surface. This zone is a kind of long delay system. The energy born in the core may spend thousands to millions of years working its way through this region before it ever reaches the sun's visible surface. That sounds surprising because light in empty space moves fast, but inside the sun it keeps bumping into matter. Each bounce changes direction and slows the overall journey. The radiative zone is important because it acts like a bridge between the core and the outer part of the sun. It keeps the flow of energy steady, and it helps control how the sun releases heat over long periods of time. Without this layer doing its slow job, the sun's energy output would not move in the smooth way that it does now.
Convection zone. Above the radiative zone is the convection zone. Here, the sun changes the way it moves energy. Instead of letting energy drift outward by repeated radiation, it uses convection, which means hot material rises and cooler material sinks. This layer is full of rolling motion. Hot plasma near the bottom becomes less dense and rises upward. As it rises, it cools and becomes heavier, then sinks again. This creates giant loops inside the sun, like a huge pot of water slowly boiling from below. The motion is not random. It is the sun's way of moving energy when radiation alone no longer works well. The convection zone is also the place where the sun's surface patterns begin to form. The top of each rising cell helps create the grainy texture seen on the photosphere called granulation. Those small bright patches and darker lanes are the surface signs of the powerful movement below. The convection zone also helps drive magnetic activity, which later shows up as sunspots, flares, and other solar events. Photosphere. The photosphere is the visible surface of the sun. When people say they are looking at the sun, this is the layer they are actually seeing. It is not a solid surface. It only looks like a surface because it is the point where the sun becomes transparent enough for most of its visible light to escape into space. The photosphere is cooler than the layers below it, but cooler is only relative. Its average temperature is around 5,800 Kelvin, which is still hot enough to make the sun shine brightly. This is the layer that sends most of the sunlight we receive on Earth. It is the sun's public face, the part that defines how we picture our star in everyday life. Even though the photosphere looks smooth from far away, it has structure. Its surface is covered with small bright cells and darker edges caused by convection below. It is also where sunspots appear, and these dark regions are linked to strong magnetic fields that block some of the rising heat. So the photosphere is not quiet at all. It is the visible top of a very active star.
Chromosphere. Above the photosphere is the chromosphere. This is a thin, reddish layer of the sun's atmosphere, and it is much harder to see because the photosphere below it is so bright. The name comes from its color, which can appear as a red glow during a total solar eclipse. The chromosphere behaves in a surprising way. As you move upward from the photosphere, the temperature does not simply keep falling. Instead, it begins to rise again. This makes the chromosphere one of the more puzzling layers of the sun. It seems thin and delicate, but it is full of energy, motion, and magnetic activity. Spicules, jets, and other fast-moving structures can rise through this layer as magnetic fields push hot gas around. In eclipse images, the chromosphere can look like a bright ring with tiny spikes around it. Those spikes are signs of the sun's restless atmosphere. The chromosphere is a transition zone between the dense visible sun and the far more extreme outer atmosphere above it.
Transition region. Between the chromosphere and the corona lies the transition region. This is a very thin layer, but it plays a major role in solar science. In a short distance, the temperature changes very sharply, going from the relatively cooler chromosphere to the much hotter corona. This sudden jump is one of the biggest mysteries in the sun. Scientists still study how energy moves through this narrow zone and why the heating becomes so intense so quickly. It is a tiny layer with a huge job. It helps separate the visible lower atmosphere from the very hot outer atmosphere, and it may hold clues about how the sun's magnetic fields move energy upward. The transition region is difficult to observe directly because it is so thin and so dynamic. It changes fast, and the sun's brightness makes it hard to isolate. But it matters because it sits at the boundary where the sun becomes much stranger. Once you cross it, you enter the corona, where the rules feel very different.
Corona. The corona is the outer atmosphere of the sun, and it is one of the most famous parts of our star. It stretches far into space, thinning out as it goes, and it does not have a clean edge. Under normal conditions, it is hidden by the intense brightness of the photosphere, so we usually need a total solar eclipse or special instruments to see it. The corona is strange because it is much hotter than the layer below it. While the visible surface is around 5,800 Kelvin, the corona can reach hundreds of thousands or even millions of Kelvin in some regions. That seems backward at first. Usually, things get cooler as you move away from the heat source, but the sun's corona breaks that expectation. Scientists have spent a long time trying to explain this. Magnetic fields seem to play a key role. Energy from the sun's tangled magnetic activity may be carried upward and released in the outer atmosphere, heating the corona to its extreme temperatures. Even now, this is still an active area of research. The corona also matters because it is the source of the solar wind. That means the sun is not just shining from one point in space. It is constantly sending out charged particles that fill the solar system and shape the space environment around Earth and the other planets around Earth. During strong solar events, coronal activity can help drive space weather that affects satellites, communication systems, and power grids.
Solar wind. The solar wind is the stream of charged particles flowing outward from the sun's outer atmosphere. It is not always listed as one of the main layers, but it is a natural extension of the corona and one of the most important ways the sun influences the space around it. In a way, the sun does not stop at the corona. Its reach continues far beyond that through the solar wind. This flow is constant, though it changes in strength. It carries the sun's magnetic field outward and creates a vast bubble in space around our solar system. That bubble is part of what keeps the local space environment shaped by the sun rather than by the wider galaxy. So when we talk about the sun's layers, we are really talking about a system that extends outward into space and keeps going. What makes the sun so fascinating is that each layer behaves differently. The core makes the energy, the radiative zone moves it slowly, the convection zone churns it upward, the photosphere lets light escape, the chromosphere adds color and motion, the transition region marks a sharp change, and the corona opens the sun into space. Together, these layers turn the sun into a living, changing star rather than a simple glowing ball.